In this video, I will present perfusion imaging using dynamic susceptibility contrast. My name is Uğur Güler and I am doing this for my MRI project. Magnetic resonance imaging is done using the difference between T1 or T2 values among the tissues, like the white matter or the gray matter of the brain. The difference between the T1 and T2 values causes a contrast in the received signal between the tissues, and the image it corresponds to a brighter side or a darker side. To image the perfusion, we also need to use the contrast similar to this. However, we cannot acquire the contrast from T1 or T2 values, as over time the T1 or T2 values in the blood doesn't change significantly. To introduce contrast, we inject gadolinium-based contrast agents to the patient. Gadolinium is a paramagnetic metal ion which aligns its magnetic field to the present magnetic field in the ambient. So, the parts where the gadolinium is presented has different magnetic field than the other parts. Let's say B0 is our main field. In the part where the gadolinium is not present, B0 is effective and the B0 is effective. However, where the gadolinium is present, the total B will be B0 plus B gadolinium. This will cause the Larmor frequency to change, as the Larmor frequency is the coefficient times the presented magnetic field. The Larmor frequency needed to excite the water molecules here will be different from here. This will cause dephasing, and dephasing will decrease the received signal strength in the areas where the gadolinium is present. The received signal can be formulated as S0 times exponential to R2 times TE. R2 is 1 over T2 value. The T1 value is ignored as the imaging using dynamic susceptibility contrast is done on T2 weighted images. When gadolinium is presented, R2 value is changed into original R2 plus some constant of gadolinium and the concentration of gadolinium. So this changes our signal into this, and if we divide the original signal with new gadolinium in affected signal, we can derive the concentration of gadolinium over time. In this plus, we can actually observe the process better. In here, assume that we are taking fast images over time in small time intervals. When the gadolinium is not presented, the received signal will not change significantly, so it will be a constant line. However, when the gadolinium passes through the part of the blood, the received signal strength will decrease sharply, and over time it will start to recover as the gadolinium will start circulating through the body. In the B part, we can see the concentration plot, which is acquired from the formulation here. As you can see, when the signal is dropped, the concentration increases, and when the signal is recovered, the concentration starts to decrease. We can roughly estimate the blood volume, this is cerebral blood volume, by the integral under the area under the plot of the gadolinium. However, this is not the absolute value, as gadolinium is not disposed from tissues completely. A small part of it still remains, so the signal strength will not go to the same level as before. To calculate the real value of cerebral blood flow and the blood volume, we take the convolution of arterial input function, which is the acquired gadolinium concentration among the major arteries, and the tissue residue function. Tissue residue function is a response of the gadolinium disposed among the tissues. From here, we can take out the cerebral blood flow, and if we take the integral of the blood flow, we will get the blood volume. and to compute the mean transmit time, we will divide blood volume over blood flow, and we will get our desired values. In this image, we can more easily see the effects of the images. In this part, this is an image of a dead brain, and in this part, there is no blood flow, as you can see. The arteries are damaged, so there is no blood being transmitted here. The blood flow value is purple. Some areas are red, some are blue, some are green. The red area means the flow is fast, and the blue area means the flow is less. The purple area, where the brain is dead, has no blood flow. So we can actually estimate that the blood volume will also be really low. And here we can see that the blood volume is also really low because they are correlated with each other. Time to peak value is the time required for a signal to drop to its minimum value, or the concentration to achieve its peak value, which is also dependent on mean transmit time. We can see that the time to peak is really high here, which is close to the dead part, and in the dead part we cannot actually compute the time to the peak value because there is no peak or minimal locations, as there is no blood passing through there. The start level of the signal strength, let's say this is the plot of signal, it will not change because there is no gadolinium-based contrast agents passing through there, significantly changing the received signal. So there will be no contrast and there will be no image there. Thank you for listening to me. Goodbye.